Bowling balls. We've all seen the pros throw them on TV, and it seems like they always strike every time. What is common in all pro bowlers is that they curve or hook the ball with their release. So why and how do they do it? To explain this, let's start out with some basic knowledge. With 60 feet from the foul line to the first pin, bowling lanes are usually layered with a thin film of mineral oil for the first 2/3 of the lane. That means that 40 feet from the foul line, the lane is no longer oiled and feels similar to a gym floor. This is important since bowling balls skid through the oil from the reduced kinetic friction on the surface of the lanes. Once it hits the dry part of the lane with no oil, the bowling ball is able to generate friction, and any angular rotation placed on the ball will result in a change of ball direction that travels in a similar plane of rotation, which creates the curve we see. Bowlers hook the ball because this allows them to have their bowling ball hit a certain area, called the pocket, at the optimum angle of 3 to 6 degrees from the middle of the lane to achieve the best chance at getting a strike. Bowling balls are able to achieve a curve through two general mechanisms. First, the bowler applies an angular rotation on the ball by pulling one side of the ball with the fingers at the point of release, seen here. Second, the ball's internal core and external surface are engineered so that the ball is able to achieve the three phases of ball motion: skid, hook, and roll in that order. Let's see just how both the surface and core of the ball makes this happen. At face value, the surface of the bowling ball may seem perfectly round, but a microscopic view of the surface reveals that bowling balls are actually quite porous. Small holes and cavities in the ball help to absorb the oil on the lanes as well as add treading to the surface of the ball, so that the ball is able to essentially grip the lane while the oil is absorbed through the pores. Pore sizes and the type of material dictate how well the ball responds in oil, known as the skid and hook phase. In these two shots, both bowling balls are traveling in the same initial direction and location, but one bowling ball is made of reactive resin, a highly porous material, while the other ball is made of polyester plastic, which is much less porous. As you can see, the reactive resin ball is much better at generating friction, which allows for a greater change in direction in the hook phase. The core of a bowling ball features a dense block that varies in shape and size. By drilling holes into the bowling ball at different places, an uneven distribution of the mass in the bowling ball is created. As a result, the bowling ball rotates along an uneven axis. Near the end of the lane, the angular rotation of the ball is able to fully translate into a change in ball direction, and the ball will lose its axial rotation and roll in almost a straight angle to the pocket during the roll phase. This is advantageous as this will allow the ball to drive through the pins, rather than deflect off the middle pin, as seen here. Be sure to watch the direction the ball travels after it hits the first pin. The first ball drives through the pins because it is in roll phase and travels to the left of the middle pin. The second ball glances off the first pin because it hits the pin while still in hook phase, and the core distributes the mass towards the right side of the ball. As engineers improve the chemical and physical composition of bowling ball surfaces and cores, we have been able to create bowling balls that can not only curve, but create various ball motions that are used and desired with different oil patterns placed on the lane. Thank you for watching, and go bowling!